With your head wrapped around routing, we'll now take a look at the nuts and bolts that make routing possible: naming, addressing, and forwarding.
And you'll start your first significant Mininet project. In the project, you'll investigate switch buffer sizing, which can have an important effect on network performance.
In this lesson, we will be covering IP addressing. In particular, we will be covering IPv4 address structure and allocation. IP stands for Internet Protocol, and version 4 is the version of the protocol that is widely deployed on the Internet to date. Each IP address is a 32-bit number, and that 32-bit number is formatted in what is called dotted quad notation. For example, the IP address for www.cc.gatech.edu is 130.207.7.36. Now this is just a convenient way of writing a 32-bit number. So 130 represents 8 bits, and 207 is another 8-bit number. 7 is another 8-bit number, as is 36. This structure allows for 2 to the 32, or about 4 billion, Internet addresses. Now that sounds like a lot of addresses. As it turns out, it's actually not enough, and we're running out of IP addresses, as I'll discuss in a later lesson. But even if we only had to deal with 2 to the 32 Internet addresses, that's still a lot. Think of if you have to store every single IP address as an entry in a table. Very quickly that becomes an extremely large table, where lookups can be slow, and the memory required to store such a large table might be expensive. So what we need is a more concise way of representing groups of IP addresses. There are different ways to group IP addresses, and we'll look at the prevailing method in the next part of the lesson. But first, let's look at how this was done before 1994. Before 1994, addresses were divided into a network ID portion and a host ID portion. So if we take our 32 bits, suppose the first bit is a 0, note that that's half of all IPv4 address space. Anything that starts with a 0 is going to be known as a Class A address, and the next 7 bits will represent the network ID, or the network that owns this portion of address space. The remaining portion of the address space is dedicated for hosts on that network. In this case, any Class A network can support up to 2 to the 24th hosts. Addresses that started with 10 were designated as Class B networks, where the first 16 bits signified the network ID, and the remaining 16 bits signified the host ID for that network. Note here that each Class B address range represents about 1/65,000th of all Internet address space. So discounting the first 2 bits, which indicate that this is a Class B network, we have about 2 to the 14th unique Class Bs, each of which can have 2 to the 16th or 65,000 hosts on each network. Class Cs use the first 24 bits for the net ID and the remaining 8 for a host ID. So each Class C network essentially can only have 255 hosts on it. This plot shows the BGP routing table size as a function of the year, starting in 1989 and going up to 1994. You can see that at this time, the Internet routing table is quite small. It started at less than 5,000 prefixes. By comparison, now we have about 500,000 IP prefixes in the Internet routing table. But we can see in this period that Internet routing table growth began to accelerate. In particular, the growth rates were exceeding the advances in hardware and software capabilities, and in particular, we began to run out of the Class C address allocation. There were far more networks that needed just a handful of IP addresses, such as a Class C address space could provide, and yet because only a certain range of the IP address space could be used for Class C addresses, we began to run out fairly quickly. So there began to be a need for more flexible allocation. The solution to this problem was something called classless interdomain routing, or CIDR, something that we'll cover in the next lesson. As a quick quiz, suppose you have Class A address space, which means that the network ID is 8 bits. How many hosts can a single Class A network support? Is it 2 to the 8th, 2 to the 16th, 2 to the 24, or 2 to the 32? Each Class A address space has a network ID of 8 bits, meaning that there are 24 bits that remain for the host ID. This means that each Class A network can support up to 2 to the 24th hosts. Let's take a look at how IP address space is allocated to Internet service providers. At the top of the hierarchy is an organization called the Internet Assigned Numbers Authority, or IANA. IANA has the authority to allocate address space to what are called regional routing registries. For Africa, the regional registry is called AFRINIC. For Asia and Australia, the registry is called APNIC. For North America, it's ARIN. For Latin America, it's LACNIC. And for Europe, it's RIPE. ARIN, in turn, allocates address space to individual networks, like Georgia Tech. The address space across registries is far from even. Now, this graph is from a journal article that's a little bit dated now, but it gives you an idea of how many /8 address allocations have been allocated to each of the regional registries. So as of 2005, North America had 23 /8s allocated to it, but the entire continent of Africa had only 1. Now, recent news is that IANA actually finished allocating all remaining /8 Internet address blocks, essentially meaning that we're out of IPv4 address space. So when you hear that we're out of IPv4 addresses, it doesn't mean that you can no longer attach a new device to the Internet. There are various ways for coping with this pressure on address space. What that means is that IANA no longer has any more /8 blocks to give to these regional registries. Querying an IP address using whois in a routing registry, such as ra.net, will tell you the owner of that particular prefix. For example, if we run a whois query on an IP address at Georgia Tech, it will tell us that that IP address is from a /16 allocation, that Georgia Tech is the owner of the prefix, and it's associated with this autonomous system number. The routing registry entry also gives us some additional information, such as who to contact if we need to contact the owner of this address space. The pressure on address space usage spurred the adoption of classless interdomain routing, or CIDR, which was adopted in 1994. The idea is that instead of having fixed network ID and host ID portions of the 32 bits, instead we would simply have an IP address and what is known as a mask, where the mask is variable length and indicates the length of the network ID. So for example, suppose we have an IP address like 65.14.248.0/22. Well, in this case, our 32 bits look like so, but this doesn't tell us how long the network ID and how long the host ID should be. The /22 indicates the mask length, which says that the first 22 bits should represent the network ID. Now the key is that this mask can be variable length, and the mask length no longer depends on the range of IP addresses that are being used. This allows those allocating IP address ranges to both allocate a range that's more fitting to the size of the network and also not have to be constrained about how big the network ID should be depending on where in the IP address space the prefix is being allocated from. Of course, now the complication is that it's possible to have overlapping address prefixes. For example, 65.14.248.0/24 overlaps with 65.14.248.0/22. The red prefix is actually a subset of the black one. So supposing these two entries both show up in an Internet routing table, what are we supposed to do? The solution is actually to forward on what's called the longest prefix match, meaning that if a routing table has two overlapping entries, that it should forward according to the entry that has the longest prefix, or the longest mask length. Intuitively, that makes sense because the prefix with the longer mask length is more specific than the prefix with the shorter mask, or the larger prefix. Let's take a closer look at longest prefix match. So each packet has a destination IP address, which determines where the packet should be forwarded next, and a router basically looks up a table entry that matches that address. So for example, a forwarding table might have a number of prefixes in it, and many of these prefixes might be overlapping. But when we see an IP address that may match on one or more prefixes in this table, we simply match that IP address to the entry in the forwarding table with the longest matching prefix. So the benefits of CIDR and longest matching prefix are efficiency, since prefix blocks can be allocated on a much finer granularity than with classful interdomain routing, and the opportunity for aggregation if two downstream networks with more specific or longer prefixes should be treated in the same way by an upstream network, who might simply aggregate two contiguous shorter prefixes into one forwarding table entry with a shorter prefix. For example, a benefit for aggregation might exist if two downstream networks, A and B, each had /16 address space allocated to them, but upstream, all the traffic always came through the same upstream network, C. If the rest of the Internet only reached A and B via C, then the rest of the Internet need only know about C's address space, which might be 12/8. This might allow the upstream network to simply aggregate or not announce these more specific prefixes, since they're already covered by the less specific upstream prefix. Now, CIDR had a significant effect on slowing the growth of the Internet routing tables from 1994 to 1998. So from 1994 to 1998, we see roughly linear growth in the number of prefixes in the Internet routing table. Around 2000, fast growth in routing tables resumed. You can see that growth here, once again, started to pick up. A significant contributor to this growth was a practice called multi-homing. Multi-homing can actually make it difficult for upstream providers to aggregate IP prefixes together, often requiring an upstream provider to store multiple IP prefixes for a single autonomous system. Sometimes those IP prefixes are contiguous, and sometimes they aren't. Let's take a quick look at how multi-homing can stymie aggregation. In this example, a stub AS, in this case 30308, might receive IP address space, say 12.20.249/24, from one of its providers, such as AT&T, which happens to own 12.0.0.0/8. Now in this case, AS30308 wants to be multi-homed. In other words, it wants to be reachable via two upstream Internet service providers. In this diagram, the two Internet service providers are AT&T and Verizon. To be reachable by both of these ISPs, AS30308 has to advertise its prefix, which it received from AT&T, via both AT&T and Verizon. The problem occurs when AT&T and Verizon want to advertise that prefix to the rest of the Internet. Well, unfortunately, although AT&T might like to aggregate this prefix, as I previously described, it can't. If it did, Verizon would still be advertising the longer /24 via its upstream link. And because of longest prefix match, all of the traffic would then arrive via the Verizon link, regardless of what AS30308 wanted to have happen to that incoming traffic. As a result, both AT&T and Verizon must advertise the same /24 to the rest of the Internet. This results in an explosion of /24s in the global Internet routing table. You can imagine that if a lot of stub ASs wanted to be multi-homed, then suddenly we've got a lot more /24s in the global routing table than might otherwise exist without multi-homing. Now, in a previous lesson, we looked at how AS path prepending can be used to control inbound traffic. As it turns out, longest prefix match can also be used to control inbound traffic. Suppose that ASA owns 10.1.0.0/16, and it might advertise that prefix out both of its upstream links, and that route might similarly be advertised further upstream. Now, of course, as we know from a previous lesson, given the advertisement of one prefix upstream, ASD is going to pick one best BGP route along which to send traffic back to A. But let's suppose that ASA wanted to balance that traffic across its incoming links. Well, in that case, ASA could actually advertise routes for two more specific prefixes, effectively splitting the /16 in half. So in addition to advertising 10.1/16 across both links, ASA might advertise 10.1/17 on the top link and 10.1.128.0/17, the other half of the /16, on the bottom link. Now, if either link fails, the covering /16 will ensure that the prefix remains reachable by one of the two upstream links. But because longest prefix match wins, the traffic for 10.1.128 would now traverse the bottom link, and the traffic for 10.1/17 would now traverse the top link, effectively sending traffic for half of the prefixes along the top path and traffic for the other half of the prefixes along the bottom path. Although we just explored a perfectly good reason to de-aggregate a contiguous prefix, it turns out that sometimes autonomous systems may deaggregate larger prefixes unnecessarily. A report called the CIDR report, which is released weekly, shows autonomous systems who are advertising IP prefixes that, at least according to observation, are contiguous and could be aggregated. For example, the top offender for the week of December 12, 2013 was AS6389. This single autonomous system is actually advertising more than 3,000 unique IP prefixes. The CIDR report's analysis suggests that with appropriate aggregation, this autonomous system could instead advertise only 56 unique IP prefixes. Now, this might be overly optimistic. As we just explored, there are perfectly good reasons to deaggregate a contiguous IP prefix into multiple smaller contiguous IP prefixes. But nonetheless, the report shows that there are probably a lot more IP prefixes in the global internet routing table than there could be if ASs took full advantage of aggregation. Let's have a quick quiz about CIDR. So how many IP addresses does a /22 prefix represent? 2 to the 22, 2 to the 32, 2 to the 10th, or 2 to the 8th? The /22 represents the length of the network ID, and the remaining 10 bits are for hosts in that /22 prefix. So those 10 bits reserved for the host for that /22 mean that this /22 prefix represents 2 to the 10th IP addresses. Okay, in this lesson, we will explore how lookup tables in routers are designed and how longest prefix match works. We'll explore exact match versus longest prefix match and when each is used. We'll explore IP address lookup in more depth, and finally we'll explore how longest prefix match is implemented in the form of tries. So the lookup algorithm that a router uses depends on the protocol that it's using to forward packets, and the lookup mechanism might be implemented with a variety of different algorithms or techniques. For example, MPLS, Ethernet, and ATM use an exact match lookup. Exact matches can be implemented as a direct lookup, an associated lookup, hashing, or via a binary tree. IPv4 and IPv6, on the other hand, are implemented with what's called longest prefix match. We've already looked at longest prefix match a little bit in some lessons, and in this lesson we'll look at it in a bit more detail as well as how it's implemented. It might be implemented as a radix trie, a compressed trie, which is something that we will look at in this lesson, and it can also be implemented as a binary search on prefix intervals. Ethernet-based forwarding is based on exact match of a layer 2 address, which is usually 48 bits long. The address is global, not just local to the link, and the range or size of the address is not negotiable. Now 2 to the 48th is far bigger than 2 to the 12th, therefore it's not possible to hold all the addresses in the table and use direct lookup. The advantages of exact matches in Ethernet switches is that exact match is simple and the expected lookup time is small, or O of 1. But the disadvantages include inefficient use of memory. This potentially results in non-deterministic lookup time if a lookup might require multiple memory accesses. Let's now take a closer look at longest prefix match. IP lookups find longest prefixes. Let's suppose that we want to represent a particular IP address as one point in the space from 0 to 2 to the 32 minus 1, or the range of all 32-bit IP addresses. Each prefix represents a smaller range inside this larger range of 32-bit numbers. Obviously, this is not to scale. Now, these ranges, of course, might be overlapping, as is shown here. And the idea is that longest prefix match will match the smallest prefix for which the IP address range overlaps that of the specified IP address. So longest prefix match is harder to perform than exact match. For one, the destination IP address does not indicate the length of the longest matching prefix. So some algorithm needs to determine the length of the longest matching prefix, which in this case is 21. So we somehow need a way to search the space of all prefix lengths, as well as prefixes of a given length. Suppose, for example, that we wanted to implement longest prefix match for IPv4 using exact match. Now in this case, we might take our network or our IP address and send it to a bunch of different exact match tables. And then among the tables that had a match, we would select the longest and then forward the packet out the appropriate output port. Of course, this is horribly inefficient because we'd have to have tables for each of these lengths, and every time a packet arrived, we'd have to send it to each one of these 32 tables. This is extremely wasteful of memory. An alternative is to perform address lookups using a data structure called a trie. In a trie, prefixes are spelled out by following a path from the root, and to find the best prefix, we simply spell out the address in the trie. For example, let's suppose we had the following table. Such a lookup table has entries of varying lengths. Let's see how this might be encoded in a trie. In a trie, spelling out the bit 1 always takes us to the right, and spelling out the bit 0 always takes us to the left. So to insert 111 star, we'd basically start here, 1, 1, 1, and then we insert P1, and then we repeat this process. 1, 0, star results in P2, 1, 0, 1, 0 results in P3, and 1, 0, 1, 0, 1 results in P4. If we want to insert 1, 1, 1, 0, insertion is easy. We can simply insert P5 as such. Lookups are easy. So for example, let's suppose we want to look up 1, 0, 1, 1, 1. Well, all we have to do is spell this out in the trie. So we can follow 1, 0, 1, and now we see that there's no entry for 1, 0, 1, 1. So we use the entry of the last node in the tree that we traverse that has an entry, in this case, P2. Now this structure here is what's called a single-bit trie. Single-bit tries are very efficient. Note that every node in this trie exists due to one of the 5 forwarding table entries that we've inserted in the trie. So a single-bit trie is a very efficient use of memory. Updates are also very simple. We saw how easy it was to insert the entry for P5. Unfortunately, the main problem is the number of memory accesses that are required to perform a lookup. For a 32-bit address, we can see that looking up the address in a single-bit trie might require 32 lookups in the worst case, one for each bit, since each bit in the address requires one traversal in the trie or one memory lookup. So this could be very bad. At worst, 32 accesses in the worst case. To put this in perspective, an OC48 requires a 160 nanosecond lookup, or simply 4 memory accesses. So 32 accesses is far too many, especially for high-speed links. The other extreme, of course, is to use a direct trie, where instead of 1 bit per lookup, we might have one memory access responsible for looking up a much larger number of bits. So for example, we might have a 2-level trie, where the first memory access is dictated by the first 24 bits of the address, and the second memory access is dictated by the last 8 bits of the address. Now here, we can look up an entry in the forwarding table with just 2 memory accesses. The problem is that this structure results in a very inefficient use of memory, unlike the single-bit trie. To see why, suppose that we want to represent a /16 prefix. Well, unfortunately, we have no way of encoding a lookup that's just 16 bits. We have to rather encode 2 to the 8th identical entries corresponding to the 2 to the 8th /24 prefixes that are contained in that /16. So this is an extremely inefficient use of memory. As a quick quiz, suppose we have a direct trie, and the first level is 16 bits. The next level is 8 bits, and the third level is the final 8 bits. In the worst case, how many memory accesses would be required per lookup? Because the trie has a depth of 3, in the worst case, a lookup might require 3 memory accesses. How many entries would I need to represent a /20 prefix? A /20 prefix is 2 to the 4th, or 16 /24s. And I need to basically represent 16 entries at the 24-bit level of the trie, or the second level, and therefore I'd need 16 entries to represent a /20 prefix. To achieve the memory efficiency of a single-bit trie with the fast lookup properties of a direct trie, a compromise is to use what's called a multi-bit trie, or multi-array trie. Let's start with a binary trie, where 1 bit is resolved at each node. Here, the depth is big W, the degree of each node is 2, and the stride for each lookup is 1 bit. Then we can generalize this to a multi-array trie, where the depth is now W over K, if the degree is 2 to the K, and each level resolves K bits. The binary trie is a simple case of the multi-array trie, where k equals 1. Let's take a look at the 4-array trie, where k equals 2. Suppose we have the same forwarding table as before, but now each node in the trie is responsible for resolving 2 bits. So if we take 1, 1, and now we take 1 star, that's 1, 0, and 1, 1, and now we basically have to put P1 in 2 places in the tree. 1, 0 star results in just 1 entry. 1, 0, 1, 0 star results in 2 traversals. And 1, 0, 1, 0, 1 star again represents 2 entries for 1, 0, 1, 0, 1, 0 and 1, 0, 1, 0, 1, 1. Now suppose we want to look up 1, 0, 1, 1, 1. Again, we can spell this out, 1, 0, 1, and we can see that we get no further than P2, and again, we match at P2. One thing we can do to save space further is create what's called a leaf-pushed trie. In such a setting, we can save ourselves some space. Instead of having these pointers, we can push these entries into the left and right side of this node, respectively. So 1, 0 becomes P1 on the left side, and 1, 1 becomes P1 on the right side. There are a variety of other optimization algorithms, including one called Lulia and another called Patricia. Each of them use the same basic idea that we've explored here, except some of them, like Lulia, are a 3-level trie, and often they use a bitmap to compress out repeated entries, such as those that exist here. Now there are alternatives to implementing longest prefix match with the trie. One could start with a content addressable memory, or a CAM. Now a CAM is a hardware-based route lookup where the input is a tag and the output is a value. So for example, the tag might be an address and the value might be the output port. Now the CAM really only supports exact match, but it is an O of 1 lookup. There's something called a ternary CAM, though, where instead of exact matching in the tag, you can have 0, 1, or don't care, or a star. The ternary CAM, and in particular its support for a wildcard, permits an implementation of longest prefix match. One can thus have multiple matching entries, but prioritize the match according to the longest prefix in the ternary CAM. Let's now talk about various problems that resulted from IPv4 and the growth of the Internet routing tables, and 2 different solutions to Internet routing table growth: Network Address Translation, or NAT, and IPv6. So the main problem that we are seeing is that IPv4 addresses have only 32 bits, which means that there can only be a total of 2 to the 32 unique IP addresses. Not only that, as we've seen, IP addresses are allocated in blocks, and fragmentation of this space can mean that IPv4 addresses can be quickly exhausted. In fact, we've already seen the last /8 from IPv4 address space allocated to the registries. So we're well on our way towards running out of IPv4 addresses. In some sense, you can say that we've essentially already run out. In this lesson, we're going to look at 2 solutions: Network Address Translation, or NAT, and IPv6, whose main feature is 128-bit addresses. Let's first take a look at NAT. NAT allows multiple networks to reuse the same private IP address space. Let's suppose that we have 2 networks. These networks might be, for example, homes, or they might be larger networks in regions of the Internet where IPv4 address space is scarce, for example, in developing regions. What NAT allows these networks to do is reuse the same portion of Internet address space. For example, a particular special private IP address space is 192.168/16. Other private IP address space is specified in RFC 3130. Now obviously these 2 networks couldn't coexist on the public Internet because routers wouldn't know if they got a packet destined for an IP address in this space, which network the packet should be sent to. What a NAT, or a network address translator, does is take the private IP addresses that are behind the NAT and translate those IP addresses to a single globally visible IP address. Now to the rest of the Internet, Network 1 appears to be reachable by a single IP address, 203.178.1.1, and Network 2 is reachable via a single distinct global IP address, 133.4.1.5. Now a host back here, say 192.168.1.10, might send a packet towards a global Internet destination. Now the key behind NAT is that this packet has a source port, and the NAT is basically going to take that source IP address and port, and it's going to translate it into a publicly reachable source IP address and port, and the destination will remain the same. That packet will make its way to a global destination, and the reply will make its way to the globally reachable IP address on the corresponding port. Now when that packet with that particular destination IP address and port reaches the NAT has a table that knows the mapping between that public IP address and port and the private one that it rewrote to generate the corresponding public IP address and port. So it can simply now rewrite the destination IP address of this packet to the corresponding private address and port. NATs are popular on broadband access networks, small or home offices, and VPNs. There's a clear savings in IPv4 address space since there can be many devices in one of these private networks, and yet all of the devices that are behind the NAT only use up one public IP address. The drawback, of course, is that the end-to-end model is broken. Now, we talked about the end-to-end model in a previous lesson, and let me just remind you how NAT breaks it. If the NAT device failed in this instance, for example, the mapping between the private source IP address and port and the public source IP address and port would be lost, thereby breaking all active connections for which the NAT is on the path. It's also asymmetric. Under ordinary circumstances, it's rather difficult for a host on the global internet to reach a device in a private address space in network 1 or network 2 because by default those devices in these private networks do not have public globally reachable IP addresses. So NAT both breaks end-to-end communication and it also breaks bidirectional communication. Another possible solution to the IP address space exhaustion problem is to simply add more bits. This is the gist of the contribution of the IPv6 protocol. Here's a picture of the IPv4 protocol header, and all of the fields shown in red have basically been removed in IPv6, resulting in both a much simpler header and addresses that are much larger. By contrast, here is the IPv6 header. The IPv6 header provides 128 bits for both the source and destination IP addresses. Now the format of these addresses are as follows. Of the 128 bits, the top 48 bits are for the public routing topology, and we have a 16-bit site identifier, and finally a 64-bit interface ID, which effectively has the 48-bit Ethernet address of the interface, plus 16 more bits. Now the top 48 bits can be broken down further. They include 3 bits for aggregation, 13 bits for a top-level provider, something like a Tier 1 ISP, 8 reserved bits, and 24 additional bits. Now note that there are 13 bits in the top 48 that directly map to the Tier 1 ISP, meaning that addresses are purely provider-based. Thus, changing ISPs would require renumbering. IPv4 has many claimed benefits. There are more addresses, the header is simpler, multi-homing is supposedly easier, various aspects of security are built in, such as the IPv6 crypto extensions. Now, despite all of these benefits, we've yet to see a huge deployment of IPv6 yet. Now, despite all of these benefits, we've yet to see a significant deployment of IPv6. Here you can see the number of routing table entries for IPv6 routes, as well as the growth over time from 2004 to the end of 2013. What's remarkable is that we only see 16,000 IPv6 routes in the global routing table. This is not that many, considering that there are about 500,000 IPv4 routes in the global routing table. The problem is that IPv6 is very hard to deploy incrementally. Remember our discussion of the narrow waist. Everything runs over IPv4, and IPv4 was designed to run over a variety of physical layers. This common protocol has allowed tremendous growth, but because everything depends on the narrow waist of IPv4, and because IPv4 is built on top of so many other types of infrastructure, changing it becomes extremely tricky. Incremental deployment, where part of the internet is running IPv4 and other parts have been upgraded to IPv6, results in significant incompatibility. There are various incremental deployment options for IPv6. One is what's called a dual stack deployment. In a dual stack deployment, A host can speak both IPv4 and IPv6. It communicates with an IPv4 host using IPv4 and communicates with an IPv6 host using IPv6. What this means is that the dual stack host has to have an IPv4 compatible address. Either the host has both an IPv4 and an IPv6 address, thus allowing it to speak to an IPv4 host, or it must rely on a translator, which knows how to take a v4 compatible IPv6 address and translate it to the v4 address. One possible way of ensuring compatibility of a v6 address with IPv4 is simply to embed the IPv4 address in 32 bits of the 128 that are allocated for the IPv6 address. Now, a dual stack host configuration or a v4 compatible IPv6 address solves the problem of host IP address assignment, but it doesn't solve the problem that IPv6 deployments might exist as islands. For example, multiple independent portions of the Internet might deploy IPv6, but what if the middle of the network only speaks and routes IPv4? Well, the solution here is to use what's called 6-to-4 tunneling. In 6-to-4 tunneling, a v6 packet is encapsulated in a v4 packet. Now that v4 packet is routed to a particular v4 to v6 gateway corresponding to the v6 address that lies behind that gateway, and at this point, the outer layer of encapsulation can be stripped and the v6 packet can be sent to its destination. This, of course, requires the gateways at the boundaries between the v4 and v6 networks to perform encapsulation of the packet as it enters the v4 only part of the network and decapsulation as the packet enters the v6 island where the destination host resides.